Okay, let's take a quick look at this question, which says for each of the following bytes represents an integer in 2's complement form. State the denary value that belongs to this bit pattern. Okay, 0111 0111. What is the denary value for this? Okay, let me quickly write down the number here, 0111 0111, and apply the weights 1 2 4 8 16 32 64 and minus 1 to 8. So this becomes what? This becomes minus 128 into 0 plus 64 into 1 plus 32 into 1 plus 16 into 1 plus 8 into 0 plus 4 into 1 plus 2 into 1 plus 1 into 1, right? So this is equal to 0 plus 64 plus 32 plus 16 plus 0 plus 4 plus 2 and plus 1. So this is going to be equal to 119. So the result is 119. Let's solve this one real quick. 1 triple 0 1 triple 0 1 triple 0 1 triple 0. Once again we have to apply the weights 1 2 4 8 16 32 64. Remember, in 2's complement the final weight is always negative, so this is going to be minus 128 plus 0 plus 0 plus 0 plus 8 plus 0 plus 0 and plus 0. Effectively what we have is minus 128 plus 8, and the answer comes out to be minus 120. Next we have to express the following integer in 2's complement form. So minus 17 has to be represented in 2's complement form. So we have minus 17, right? And the way I like to do this is to write this value 17, basically write positive 17 in binary form. So how are we going to write positive 17 in binary form? 1 2 4 8 16 32 64 and minus 1 to 8. And to write 17 we are going to use 16 plus 1 is 17, and all the other bits are going to be 0. So this is plus 17, this is plus 17. Now we are going to apply 1's complement, and by 1's complement we mean we are going to flip or invert all the bits. So we are going to write, we're going to replace zeros with ones and ones with zeros. So this becomes a 1, this becomes a 1, this becomes a 0, and this becomes this one becomes a 1, right? This is a 1, right? And this one becomes a 0, this becomes a 1, and this becomes a 1, and this becomes a 1, and this one becomes a 0, right? So this here is the 1's complement. Okay, this here is the 1's complement. What we can do is we can add 1 to this value to give us the 2's complement. 1 plus 0 is going to give us 1, and we're going to copy the rest of the value 1 1 1 0 1 1 1. So this is minus 17 in 2's complement form. Okay, remember, to find 2's complement form, let me give you another example real quick. If you have the number 36, for example, minus 36, how are we going to convert it into 2's complement? We are first going to write plus 36, and to write plus 36 we'll write down the weights minus 128 64 32 16 8 4 2 1, and because we want to write plus 36, so this is going to be 1 and this is going to be 1. These are going to be zeros, 0 and 0. Now this is plus 36, right? We are going to flip this and this flipping is basically called ones complement. So we are going to convert this above number into ones complement, and this becomes what? 1 1 0 1 1 0 1 1. Okay, so now we have the ones complement. We need to add 1 to it. When we add 1 to ones complement, then this becomes 2's complement. Okay, so 1 plus 1 is going to give us 0 as the sum and 1 as the carry. 1 plus 1 is going to give us 0 as the sum and 1 as the carry. 1 plus 0 is going to give us 1, and we can copy the rest of the values down. 1 1 0 1 1. So this is minus 36. You can cross check it whether this is minus 136 or not. Write down this number 1 1 0 1 1 1 0 0 and apply the weights. 1 2 4 8 16 32 64 minus 1 2 8. When you do your additions, this becomes what? Minus 128 plus 64 plus 0 plus 16 plus 8 plus 4 plus 0 plus 0. Now this equals what? This equals 64 plus 16 is 80 plus 8 88 plus 4 92. So this becomes equals to minus 128 plus 92. And when we solve this, this becomes equals to, this equation equals minus 36. So what we carried out here is the way that a computer converts a positive number into a negative number and a negative number into a positive number. What we did was we wrote the number down in binary form, right? The positive number down in binary form. So we had minus 36 to start with, but we wrote down plus 36 in binary form. We took the ones complement, so this is the ones complement. Then we added 1 to it to get the 2's complement. So this is basically the 2's complement. Okay, going back, this was what we had calculated for minus 17, and let me write the answer down. So minus 17 in 2's complement is written down as 111 0 1 1 1 1. Okay, let's move on. Now he says state in denary the range of integer values that is possible to represent in 2's complement using a single byte. Okay, so the lowest value would be the highest negative value possible, right? So basically what we have is a byte, right? So we have 8 bits, 1 2 3 4 5 6 7 8. Okay, and we have to write down the lowest possible value. Now the lowest possible value would obviously be negative, and it would be the highest negative value possible, right? Because if we have minus 1, right, and we have minus 2, this value is lower than this value, right? And likewise minus 3 is lower than minus 2. So what is the most negative value that we can write? To write down the most negative value, we are going to first apply the weights. Minus 128, 64, 32, 16, 8, 4, 2, and 1, right? 1, 2, 3, 4, 5, 6, 7, 8, right? So these are our 8 bits. To write down the most negative value, I'll select 1 here, minus 128, and I'll just put zeros to all the positive values, right? These are all positive bits, right? So I'm going to use 0 here, which means what? My most negative value can be minus 128. So this is the lowest possible value that we can achieve through a single byte in 2's complement. So the lowest value is going to be minus 128. And what about the highest value? The highest value is going to be the highest positive value that we can have with 8 bits. Okay, once again we have 8 bits, 1 2 3 4 5 6 7 8. We're going to apply the weights, 1 2 4 8 16 32 64. Once again, because this is 2's complement, we are going to use a negative weight here. And now we want to write down the maximum possible positive number, because that's going to be the highest value. So we are not going to use the negative value, and we want to use 64, and we want to add 32 to it to make the number larger. We want to use 16 also. We want to use all of these because we'll get the maximum possible positive numbers by using all of these positive bits, right? So we'll get 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. This is going to give us our maximum possible positive value, and this comes out to be 127. So the answer here is 127. This is the maximum possible positive value, or the highest value that can be written in 2's complement, using a single byte, meaning using 8 bits. Okay, convert the following denary integer into BCD, binary coded decimal, 653. Okay, so we are going to be using BCD, right? 653. Remember, BCD uses a nibble. Nibble means 4 bits. So, and BCD values can be between 0 and 9 only. So we can use these 4 bits to represent a value between 0 and 9. Meaning what? Meaning if we want to represent 6, we are going to use 4 bits for this 6, and if we want to represent 5 in BCD, we are going to use another 4 bits, and if we want to represent this 3 in BCD, we are going to use another 4 bits. Okay, so let's apply our weights, and remember, this is not in 2's complement. This is not in 2's complement, so the final weight is also going to be positive. 1, 2, 4, 8 for these 4 bits, 1, 2, 4, 8 and 1, 2, 4, 8. Okay, let's write down 6. 4 plus 2 is 6. So this basically comes out to be 0, 1, 1, 0. We want to write 5. So 1, 0, 1. 4 plus 1 is 5, and this is also going to be 0. So this is going to be what? 0, 1, 0, 1. And how about 3? 3 is 2 plus 1, 3. And we are not going to use these, right? So this is going to be what? 0, 0, 1, 1. So that's your answer in BCD. Remember, BCD is represented using nibble. Nibble means 4 bits. And what is the maximum possible value in BCD? 9. So our final answer is 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1. Fine. Let's now take a look at this question. This question says that a 3-digit BCD representation has incorrectly been copied. It is shown as this, right? State how can you recognize that this is not a valid BCD representation. Okay, let's take a look. Well, these 4 bits make up the first digit, these 4 bits make up the second digit, and these 4 bits make up the third digit. When we convert this by applying weights, 1, 2, 4, 8, this comes out to be 4. When we convert this by applying weights, 1, 2, 4, 8, this comes out to be what? This comes out to be 14, and we can instantly see that there is a problem, because BCD value can only be between 0 and 9. Any value greater than 9, if a nibble equals any value that is greater than 9, then that is an invalid BCD number. BCD digit cannot be bigger than 9. Okay, let's check this one also. By applying weights, 1, 2, 4, 8, this one equals what? 2. So we can recognize that this is not a valid BCD representation, because second digit has a value of 14. BCD digit cannot have a value more than 9. Next is, it says describe a practical application where BCD is used. Well, BCD is used in digital displays. In digital displays, in calculators, or you can say digital watches, and it is also used to represent currency. It is also used to represent currency values. Okay, so currency values are also represented using BCD, and I'm going to explain that at the end of this video, why we use BCD rather than real numbers or floating point representation for currency values. Why do we use BCD for currency values? I'm going to explain that later on in this video. So this should be written as, rather than writing currency values, we can say for representing currency values.